Okay, this question is about electromagnetic induction, and again, it's a really popular topic for people to request revision-wise. So I thought I'd give this question a pop. So let's have a look at it. We've got a rectangular coil rotating at constant angular velocity within a uniform magnetic field. So we're given the field strength here in Tesla. We're given the number of turns here, 270 turns. Cross-sectional area is in centimeters squared. So we've got to look out for that. And the diagram below is a simplified 3D diagram. So here's our coil wrapped around in this square. It's spinning in between these two magnetic poles. And this is the 2D representation. And here we've got the angle. Remember, we're treating area as a vector here, and we take the direction of that vector to be perpendicular to the plane in which the area is measured. So theta here is the angle between the area and the magnetic field. The flux linkage is given as 1.29 Weber turns. In each case, for theta equals -5 and +5, and we'd expect it to be symmetrical. Okay, so let's have a look at the questions. In this topic, as with quite a few areas of physics, the level of complexity of the topic isn't matched by the level of demand from the questions. So show clearly how the value of flux linkage is obtained. So flux linkage is n phi. It's the number of turns times the amount of flux passing through an area. And if we just remind ourselves that flux through an area, by the definition of field strength as flux density, it's B times that area, but also then we have to multiply that by the cosine of theta, where theta is the angle between the area and B. So arguably it's the dot product of these two. This diagram makes it really clear. If theta was 90 degrees, no flux would pass through this area, none whatsoever. So we have to have that cos theta term in. So n phi therefore can be written as B A n cos theta. That may or may not be in the formula sheet. I can't really remember. So in this case, then plugging in the numbers, 114 times, really careful here, 420 centimeters squared. So in meters squared, that's 10 to the minus 4. Yeah, number of turns, 270. Times the cosine of 5 degrees. Yeah, the cosine of 5 degrees. It's worth remembering, I guess, I don't need to tell you guys this, you're all mathematicians. Cosine of 5 degrees is equal to the cosine of -5 degrees, isn't it? That's a true fact. True fact. Yeah, so that is equal to a number, and I'm really hoping it's 1.29 Webers. I just wish I had a calculator, man. Hold on. I'm gonna, because, right, as exam technique, in show that questions, if you're asked to show, now this isn't an approximately, so it actually doesn't quite count, but in questions where you're asked to show that something, some value is approximately whatever, don't ever write the calculation and then just say equals the whatever. Always calculate the exact value, always, because otherwise you haven't shown it. You've just stated that it is. So I've got the phone calculator out here. I'm typing stuff into it. Oh God, I think I've mucked it up already. 1 point. That's a good start. 1.2878, which is equal to 1.29 Webers. In fact, it is equal to 1.29 Webers. You don't need this approximate business. It is equal to 1.29 Webers to 3 significant figures. So that's fine. Explain why the induced EMF is 0 when theta equals 0. There's a few ways we could do this. I would suggest if we think about the value of cos theta when theta is equal to 0 is 1, and that's a maximum value. So therefore the flux linkage is a maximum, and so rate of change of flux linkage is momentarily 0. So induced EMF is proportional to rate of change of flux linkage. So it's the rate of change that's important here. And like you guys know that rate of change of cos theta is sine theta, and that is equal to 0 when theta is equal to 0. But we don't need to go into those level of details. You probably don't even need to say it's a maximum. It's stating that the rate of change of flux linkage is 0 that's going to get us the mark for sure here. We're given the flux linkage rather than asked to calculate it at these two angles, 85 degrees, 95 degrees. The coil rotates 10 degrees in a time of 5.8 milliseconds. So from there to there in 5.8 milliseconds. Calculate the mean induced EMF when rotating between those two. So this is hopefully straightforward. EMF is equal to minus minus rate of change of flux linkage, isn't it? d over dt and phi. But since we're not doing differentials or anything like that, we'll go delta n phi over delta t. So that is equal to minus, so final flux linkage minus initial flux linkage. It's rotating between this and this, so the final flux linkage is minus 0.11 minus the initial flux linkage. What is wrong with me? Which is that, then divided by the time taken, which was 5.8. These are milliseconds, be careful. 10 to the minus 3. So I've got a lot of minus signs going on here. That is surely equal to 0.22 over 5.8 times 10 to the minus 3. Let's see what that is. I've got a calculator. Well, I've got my phone anyway. 0.22 divided by 5.8 times 10 to the minus 3. 37.9 volts. Fascinating. Okay, and that's it. So the key things to remember here, to realize, I guess, this definition of flux linkage, what it is, what it means, and the idea that it's the rate of change of flux linkage that causes an induced EMF. That's all that you're really ever going to get tested on here. Yeah, some of these questions will ask you to state Faraday's law and to state Lenz's law. This one does not, but what I've quoted here is in fact the law of electromagnetic induction, which is the combination of those two. That's it.